So for today, we're going to get the equivalent value of the time of, we're going to get the value of t raised to n times the u of t dt. We're going to get the equivalent of this time function into the complex frequency function using Laplace transform. So the Laplace of t raised to n u of t dt is equals to the integration of e raised to negative st multiplied by t raised to n dt, approaching from 0 to infinity. So if you're wondering where the u of t go, our u of t here is equivalent to 1, so we can disregard that. Or if we multiply it, so the values or the variables will remain. So we could come up with this is equal to this expression, t raised to n is equal to t, the integration of t raised to n times e raised to negative st dt approaching from 0 to infinity. So as you can see in the expression, or in the expression of this equation, we can solve this one using the integration by parts. So we set our u as equal to t raised to n, and the derivative of t raised to n is n t raised to n minus 1 dt. So the dv is equivalent to the e raised to negative st dt. So if we integrate it, we could get the value of v as equal to negative 1 over s times e raised to negative st. So using the equation of the integration by parts, which is uv minus the integration of v du. So by plugging those designated variables, so we can get these values: negative e raised to negative st over s times t raised to n approaching from 0 to infinity, so don't forget those limits, minus the integration of negative 1 over s times e raised to negative st times nt raised to n minus 1 dt. So in this part, we will plug in the limits, which is the 0 and the infinity, where if any value that has a negative high number will be equal to 0. That's why it's 0. And here, your t is equal to 0, and that's why we can get the 2 0. So all in all, in this equation, the value of this equation is 0. So the remaining ones is the n over s times the integration of e raised to negative st times t raised to n minus 1 dt. So in this integration, we could see that if we integrate it again, it will be recurring, or simply non-terminating integral. Therefore, we could come up with the equation that the Laplace of t raised to n is equal to the n over s multiplied the Laplace of t raised to n minus 1. So we're going to test if our equation is recurring or non-terminating. So at n is equal to 1, the Laplace of t raised to 1, or simply t, is equal to 1 over s squared, which is, if we substitute the value of n, 1 over s times the Laplace of 1, which is from the previous problem, the Laplace of 1 is equivalent to 1 over s, which is here, the Laplace of 1 is equivalent to 1 over n. So 1 over s multiplied by 1 over s is equivalent to this term, 1 over s squared. So same procedure as at n is equal to 2. The Laplace of t raised to, or t squared, is equal to the 2 over s multiplied by the Laplace of t raised to 1, or simply t, is equivalent to 2 factorial over s cubed. Since the value of our t is equivalent to 1 over s squared, so 2s multiplied by 2, the value of 2s multiplied by the value of t sub 1, 1 over s squared, is equivalent to the 2 factorial of s cubed, or this one. That's why it become factorial. And at n is equals to 3, the Laplace of t cubed is equivalent to the 3 over s times the Laplace of t squared is equivalent to the 3 factorial over s to the fourth. So if you're wondering how did this happen, 3 over s times the Laplace of t squared, which is equal to the 2 times 1 over s cubed. So 3 times 2 times 1 is equivalent to 3 factorial over s times the s cubed is equal to the s fourth. So this is the final answer for this term. So our final, so we could come up that the Laplace of t raised to n dt is equivalent to the n factorial over s raised to n plus 1, which is the equivalent value of this time function into the complex frequency function.